Hello, today I will be discussing my work into extracting parameters from MFEM simulations of cavities for use in circuit simulations. I'm doing this work under Dr. Ryan Camacho in the BYU Electrical Engineering Department and working with Keith Cartwright from Sandia National Labs. To motivate my work, suppose we have a digital electronic circuit, perhaps like the one shown here. Maybe the circuit is a clock, with different bits just oscillating between 0 and 1 in order to keep track of the time. Because we just love this circuit, we're going to bombard it with electromagnetic radiation and try to ruin its day. If our radiation is strong enough and hits the circuit just right, we could potentially cause a bit flip, which could cause a cascading effect, making the circuit be forever 2 seconds behind for all time and eternity. In addition to disrupting the information flow in this way, electromagnetic radiation could also potentially cause power problems, making some parts of the circuit get too much power and burn out, or other parts get not as much power as they need to function. Because electromagnetic radiation is a problem that people know exists, circuit designers have taken measures to try to mitigate against it. One of the most common mitigation techniques is putting your circuit in a metal cavity or box. If this metal box was perfect, it would completely isolate the circuit from any external radiation. But it's not perfect. No matter what you do, there will always be some defect, some slot that radiation can sneak through. And when it does, it will couple into the cavity's eigenmodes, which can then couple onto the circuit and cause that some detrimental effects. For this reason, Sandia National Labs, who's funding my research, is interested in being able to model the coupling between a cavity eigenmode and a circuit inside that cavity. There are a couple of major challenges with this type of modeling. For one, cavities and circuits use very different simulation techniques. For cavities, you generally want full wave simulations, such as finite difference or the finite element method that we all know and love. For circuits, those are composed of hundreds or thousands of tiny itty-bitty components. If you try to resolve all of those components in a finite element mesh and then run a simulation on it, you'd need a very fine, very large mesh that will be infeasible on even the best supercomputers. However, since each of those components only affects the fields in a very small localized area, you can usually just represent each of those with one or two numbers and string them together in a network that tells you everything you need to know. When you want to model how the circuit interacts with a larger component, for example, a long wire, you model that larger component as a string of many different circuit elements. For example, if you wanted to model two long wires right next to each other, you might use a circuit network like the one shown on this slide. The elements outlined in blue are called inductors, and they model how electric current on one wire can perturb magnetic fields to cause current on the other wire. The components outlined in green are called capacitors, and they model how charge on one wire can affect the electric field to change the charge distribution on the other wire. The component outlined in red is called the load. In an actual application, that will be replaced with a big complicated circuit. When your circuit is inside a cavity, the cavity mostly interacts with the long wire parts of the circuit. Cavities can all In 1999, Ziemanzu and Robin Sloan proposed modeling coupling between electromagnetic resonators and wires using a geometry like shown on this slide, where a single eigenmode of the cavity is represented by that loop. Different components within that loop represent how energy from that eigenmode can couple onto different parts of the wire. In order to get the parameters they need to do this, these authors did a full wave simulation of their geometry and then integrated along certain flux planes in order to get the parameters they needed for the circuit simulation. My goal is to generalize what they did to a slightly different geometry, where the wire is actually inside the resonant cavity. I'm also attempting to generalize to add another loop to the circuit so that I can model multiple different eigenmodes coupling onto the wire at the same time. In order to do the full wave simulations and get the integrals I need to do this, I'm using MFEM. Specifically, I'm using MFEM example 13, which solves the eigenmode equation shown in the center of this slide. The parameter E in this equation represents the spatial distribution of the electric field for an eigenmode. Each of these eigenmodes resonates at a specific frequency, which can be derived from the eigenvalue k squared. I got preliminary results for this for the entire cavity with a wire case, but for verification purposes, I've been mostly focused on the two-wire transmission line case that I talked about earlier, which is what I will talk about for the rest of this presentation. For that two-wire transmission line case, these are you want to integrate along certain flux planes to get the capacitance. For example, on this slide, I would integrate the electric flux along that green plane shown on the image on the right of this slide and divide by the line integral of that white line in order to get a single capacitor value. If I wanted the other capacitor values, which I do, I would repeat that integral at different points along the wire's length, in this case the z-axis in those images. Similarly, to get an inductor, I would integrate along the magnetic field along the plane shown in blue on the image on this slide. The magnetic field is not what we're actually solving for in MFEM, but it can be easily derived by taking the curl of the electric field and multiplying by some constants. Once I have it, I would integrate along the electric flux along that plane outlined in green, which approximates the current flowing down the other wire. I divide by those to get the inductance. And if I wanted the other inductances, I would do it along at different points along the wire's length. Actually doing those integrals was, at least for me, fairly difficult to do in MFEM, largely because I'm new to it. First, I tried a Monte Carlo integration technique, where I just sprayed random points along the plane I wanted to integrate, got the parameters I needed, and added them up. That took forever because, because I had, at least computationally, because for each point I had to iterate through every element to find which one it was in before I could get those values. To try and speed things up, I used the quadrature rules defined in MFEM's source code to implement a quadrature integration technique, which took a lot longer to code up but runs way faster and at this point is mostly debugged. After I did all of that, I found out that MFEM seems to provide at least some surface integration functionality. I haven't looked too far into that functionality, largely because it seems to require an installation with LAPACK, and I've had trouble getting any installations beside the basic Conda or pip versions working. So that might be something I look into in the future. But with what I have right now, I've been able to get at least somewhat close results. This slide shows the two integrals I do for a capacitance, and on the far left, the numerical capacitance I estimated at each point along the wire is shown in blue. In a perfect case, I'd expect it to match with the red line, which is the analytical capacitance, assuming the wire was an infinite length. As you see, it's not quite there, but it is pretty close. Inductance is a bit all over the place right now. I'm pretty sure that's just because I need a finer mesh, but more investigation will be needed. I also did some work to do a minor modification to that equation so I can model an insulating material called dielectrics, which is what the actual circuit board is made of and will be pretty necessary to do for an actual application. Here's some results I have for those dielectrics. You can see that that where the dielectric is in that white box affects the field distribution pretty significantly. Eventually, I'm going to stitch that together with the rest of my simulation techniques, but I haven't gotten there yet. And thank you for listening.
This talk maybe is going to be a little different. I'm going to present results that have recently been sent off to publication, which I'm pretty happy about. I think some of the Portland State students in particular have seen this talk before, and it's kind of been like coming soon to a paper near you. And so we're at that point now. I will come clean that a lot of the simulations you're going to see are MATLAB simulations using a software package that I've been developing over the last eternity. But for my next project that's starting now-ish, I am going to be using MFEM. So I wanted to use this talk and this conference as an opportunity to learn about MFEM. And I thought what might be kind of an interesting learning experience for me and maybe a nice hook for this talk for all of you is how far can I replicate my simulation results in MFEM in one day? So we'll see how far I got. But let me show you kind of the setup for this. This is the inspiration or the idea of the inspiration for this project. Maurice Herzog over there on the, I guess your right-hand side, no pun intended, because his hands are totally frozen. He was the first person who summited Annapurna. His gloves blew away during a storm in the middle of the night, and he was forced to spend the night on the mountain with no gloves. He did get back safely. The doctor said it was like shaking hands with an icicle. His hands were totally frozen. But the key to this story is that he did live. And that's because physiologically, when you are in such a scenario, your body will redirect blood flow away from the frozen appendages in order to keep your body core warm, staving off the onset of frostbite, even at, or sorry, staving off the onset of hypothermia, even at increased frostbite in the appendages and extremities. So we wanted to try to model this phenomenon. Typically, heat transfer in the body has been modeled using the Pennis Bioheat transfer equation, which you can see is just a modified heat equation. That term in orange is the special term that captures the difference between tissue temperature and the temperature of the blood that's perfusing that temperature. That warm blood brings heat into the temperature, or into the tissue rather, and that term has the effect of stabilizing the tissue temperature and bringing it into equilibrium with the blood that's perfusing that. For our purposes, we wanted to try to capture both frostbite and hypothermia. These are two different phenomena. Frostbite affects the extremities, hypothermia affects the body's core. And so we wanted to model this by coupling a PDE for tissue temperature in the extremities with an ODE that's going to model body core temperature. Also, because we want to be able to simulate that regulation of energy exchange between these two compartments as a function of the temperature in these two compartments. The coupling terms that we introduced here are going to introduce nonlinearity. So we have a nonlinear coupling model. Also, the boundary condition, we're going to use for these results a simple linear Robin boundary condition modeling heat exchange with the environment. But I could imagine a world where someone might want to use a more complicated boundary condition, like a radiation boundary condition that is itself nonlinear. And so we are going to show theoretical results that account for a potential nonlinear boundary condition as well. So the model is sufficiently complicated to capture the phenomena that we want to see. And the assumptions that we place on this model are relatively reasonable. We'd like the terms that are going to be involved to be Lipschitz, the boundary condition, because it's nonlinear, we do have to place pretty strict requirements on that. Although, again, for a Robin boundary condition, this will work just fine. And then we have some standard assumptions on the physical parameters and the source terms as well. Now, why is all this necessary? Well, if we start by kind of doing the most obvious thing, and we just use a linear coupling model between the tissue and the body core, well, that's the result I'm going to show you first and kind of show you why it fails. The purpose of this slide is to illustrate that to the extent possible, we sourced our coefficients from medical literature so that we could try to capture results as realistically as we could. In particular, the coupling term for this A term, the coupling term for the partial differential equation is coming straight from Pennis's classic work. On the flip side of that, we are having this coupling term in the ODE that is going to model the effect of blood returning back from the extremity, where we're assuming that the blood has come into equilibrium with the extremity so that the blood coming back from the extremity has the average temperature of the extremity, which is average represented right there. Some of this stuff toward the bottom I'll talk about when we get into nonlinear coupling, but it's not relevant for right now. And lastly, I will point out that for the coefficient here B that is measuring the strength of the coupling on the ODE side, well, we know that the hands have about 7% of the total blood volume, so I used 7%, 0.07 for the strength of that coupling. Now, okay, all that said, here's the result when you do this model. And, oh, okay, this is, well, it's normally a movie, but it's not playing right now. It's sometimes different machines. Let's take a look at this result, though. So what I'm showing on the left-hand side is the temperature in the body core and the average temperature in the hand over time. In the middle, this is the final temperature of the hand after we've allowed the simulation to run for 40 minutes, or simulated 40 minutes. And on the far right-hand side is the extent of frostbite, where we're measuring frostbite as any element that has an average temperature less than 0 at any point in time during the simulation. So what you can see is that, yeah, the hand has pretty extensive frostbite. Based on medical literature, if you expose the hand, I should have mentioned, we're exposing the hand to minus 40°C air temperature. At that temperature, we expect the onset of frostbite within minutes, pretty extensive frostbite after about an hour. But there is kind of a problem with this, and maybe as I've rambled on, you've spotted the problem. It's right here. After about 10 minutes, our subject has passed into unconsciousness and probably, well, certainly by this point, they haven't made it, right? This is not very realistic. This isn't the picture that Maurice Herzog presents, right, where he survived overnight in the blistering cold because his body was regulating the energy exchange. Instead, what this model is presenting is energy flowing out of the hand into the environment, being replaced by energy from the body core, which then exits into the environment. And you can see the consequences of this are dire. So I guess, wow, I have only about 2 minutes left. In a paper that's coming out very soon, I alluded to, we discretize this. We have a weak form. We discretize this. The relevant part is order 1 Lagrange finite elements on an unstructured mesh. We are doing backward Euler time stepping. So all pretty standard stuff. We did prove a stability estimate and some bounds on, in addition to the bounds on the solution, bounds on the derivatives of the solution. All that was used to help us prove a discrete stability, or well, separately, we proved a discrete stability estimate, and all of that was used to prove an a priori error estimate, where we're getting the order of convergence that you would expect for such a scheme. But the way that we're going to make this into a more realistic nonlinear model is using these ramp functions. So this is basically a tool for us to be able to turn blood flow on 100% or off 0% as a function, in this case, of the body core temperature. We have a similar sort of switch function that's going to be used for the tissue temperature in the extremity. And we're going to assemble these into nonlinear coefficients right here. So basically, I can take that coefficient A from earlier from the classic Pennis equation, and I can turn it on full strength or off as a function either of the local temperature in the tissue or the body's core temperature. The result of all of this finagling is what you see right here. After an initial dip in body core temperature, these nonlinear coefficients help us shut off the energy exchange between these two compartments, and then the body's metabolism can cause this to restore back to its original temperature. The hand, we do experience a decreased overall temperature and a small increase in the overall amount of frostbite, as you would expect. So the model works, and the theory is there to back it up as well. Lastly, yeah, we'll jump to this. My ability to do this in MFEM, again, in not quite an afternoon. This was a long day, but I did start from a total beginner's perspective, like literally had to download MFEM on my computer. I found your tutorials to be extremely useful. My advisor has a joke about coding by homotopy, so that's certainly what I did. This is the Robin boundary condition, or the boundary condition example that just was sort of homotopied into my own result. On the left, we have my original result with MATLAB. In the middle, a similar result with MFEM. You can see in the error, there are a couple of nodes where the two models simply don't agree. I'm not sure if refining the mesh would increase agreement between the two models. And that's actually MATLAB's problem, because using MFEM, I can extremely easily refine the mesh, as you all know, but then I don't have a similar way to match that in MATLAB and compare in an objective way. So I found a lot of advantages to MFEM. And again, given the fact that it took me, I think, 7 months to code my own solver from scratch to do this stuff, to get this far in an afternoon is it's very optimistic for me. You can see kind of the simplifications I had to make and then the features I did retain. I will say, I'm pretty disappointed I couldn't get the parabolic to work, and I did try really hard. That'll be next, maybe one more afternoon, and I'll have that done too. So thank you guys so much. I really appreciate your attention.
Okay. So we want to solve the Darcy problem. The discrete finite element system is given by this 2x2 system. U is velocity and P is pressure. The subvector G on the right-hand side is boundary data. And we approximate the velocity U in the Ravier-Thomas space, where the flux is continuous across interior element facets. In hybridization, we break the continuity and enforce it through a constraint. On each element, we have this new system where we've introduced a constraint matrix, C, and the constraint is being handled by a Lagrange multiplier. We abuse notation. I think of this system always as on elements. If we think about it on the global system, B and A are block diagonal, so it works out to just look at it on each element. Okay, so next we partition the block system like this. We get two equations. This matrix is invertible, so you can solve for PU and then substitute it into this equation. Okay, we solve for PU, and there should be an equal sign here. And then we substitute it in. And this is our, so we assemble this last equation into a global system for the multiplier. And we store the vectors in blue and the matrices in purple. So for each element, I store them in contiguous arrays. So what happens in hybridization, we hybridize the system, we eliminate the variables U and P, we get this system, we solve for lambda, and then we recover the original system. And so you can see in the recovery, we use this blue vector and this purple matrix that we compute on our way to getting the reduced system. So we want to save it. We don't want to compute it again. Okay, but from where does the constraint matrix C come from? So in the hybridization class in MFEM, the constraint matrix is computed using an integrator for the mixed bilinear form given here. The multiplier variable mu belongs to a normal trace space on the mesh skeleton. And in my code, I've been messing with this code for quite a while, solving the Darcy problem. The numerical integration takes most of the time to set up the reduced system. So here. So instead, we construct C algebraically to improve the setup time. The setup time in my new code is roughly 50% faster than my old code. So off the top of my head, one of the runs, if the polynomial order is 0, I was using the beam hex mesh, the 3D mesh. My old code, it took 42 seconds to assemble the reduced system. In my new code, it took 22 seconds. My new code is based on an implementation of the constructing the constraint matrices algebraically, the implementation in the library paralag. And to do this, we rely on the connectivity tables in the MFEM mesh and finite element space classes. So I'm going to go into how we construct these C guys. Okay, multiplier degrees of freedom, DOFs, which we define, correspond to velocity DOFs on interior facets. So imagine this is our mesh. We have 2 elements. The mesh class has a list of boundary elements, facets that lie on the true boundary of the mesh. And we use the list to obtain an interior facet marker. So I'm pretty sure this works. What I wanted to avoid, I'm thinking ahead to parallel. I don't want to have to think about, is this facet shared across processors or not? And I think this avoids it. By the mesh itself, it's global, so it knows what its boundary is. And so I just take everything else is going to be interior, whether or not it's on a processor boundary. So I have this interior facet marker. Okay, the finite element space has a facet, edge, or face to DOF table. For this example, this is the table. Tables are stored in compressed sparse row format, CSR format. So for example, the first velocity DOF, index 0. Let's see. Oh, sorry. So facet to DOF table. So the first facet, index 0, has 2 DOFs, so 2 minus 0, and they're given here. So 0 and 1. Those are the corresponding DOFs that lie on facet 0. So basically, if we look here, we have 0, 1, 3, 2, 5, 4, 6, 7, 8, 9. That's how it goes. So what we need is to define the multiplier DOFs. So I have this facet marker, and I have my table. So what I do is I just go through each facet, and I check, is it interior or not? So if we look at the first facet, we go here, index 0, yes, it is. So I take the 2 DOFs that lie on that facet, and I put them in an array. I accumulate them. And I just keep going down like that. For this simple example, there are no other interior facets, but if we imagine this were a 1, so we go 0, 1, 2, 3, and then so we go to the third place, and then we move over in this array to find what the actual DOFs are. We define the array indices of this array to be the multiplier DOF indices. So this array gives us a multiplier DOF to velocity DOF mapping. Okay. For each element, we assume we are given this matrix already. So we must use the velocity DOF order in the element to velocity DOF table. So this is the element to velocity DOF table. So for each element, it tells you all the DOFs. And we must use this because if you remember, in the reduced system, we have to form this matrix, at least on the left-hand side. So we need the sizes to match. For this reason, we actually need a facet velocity DOF to multiplier DOF mapping. So going the other way around from our other table that went 0, 1. And so here are the 10 facet DOFs. And you can see -1 corresponds to it's not interior facet. Okay, and then the colors, they're a little bit hard to see, but they correspond to here. Okay, so we have everything. Now we want to compute C. So what do? We march through the facet velocity DOFs, and then we use our mapping here, and then we just load it in. So we have 1 for the velocity, so we go here and we get index 1 for the multiplier DOF. What's important is that we choose the multiplier DOF order in the matrix C, unlike in the hybridization class, where it kind of has to check and some of these indices can be kind of backwards. We don't have to do that. The last thing is, what if there are interior velocity DOFs? I've highlighted them here, 10, 11, 12, 13. Well, we statically condense the element interior velocity DOFs. Because interior DOFs are numbered last, I learned that from a comment that Zanio had, like deep down in some discussion. My upside down block structure makes elimination convenient. So you might have wondered why I had like CBA instead of the other way around. And so this is how we partition the matrix when we've separated the DOFs into facet and interior. And so we end up with just facet DOFs only, and the Schur complement of AII is given here. That's it.
Thank you very much. Okay, so hello, everyone. I am Anthony Colshorn. I am a PhD student here at Portland State University. And today I'm going to be talking about implementation of implicit explicit integrators in MFEM, along with some applications and examples. Before I begin, I would like to give a couple of thank yous. First, thank you, Will, for putting on such an excellent MFEM workshop. Along with that, I want to thank LLNL because this is some of the work that I've been doing at an internship at the lab. And so I want to thank them for giving me the opportunity to work on this stuff, along with thanking Boyan for his excellent mentorship throughout this project. So to give a little bit of context, this is a bit of a project within a project, so to speak, and that'll become clear like a little bit later. So to start, I'll give some motivation. Then I'll talk about like the actual implementation in MFEM, along with some examples. So some context, implicit explicit schemes are used extensively to solve time-dependent ODEs, especially in the context of, for example, like fluid flow or heat transfer. And the idea is, suppose you have a time-dependent ODE, say you have like one part, say like F1 and another part F2. And F1 might be pretty difficult to integrate implicitly, right? So for example, let's say it's nonlinear or something like that. But meanwhile, F2 is stiff, right? So you do want to integrate that implicitly. And so what might be for you is some sort of IMEX implicit explicit scheme. And here I list like a couple of different examples. So maybe the like simplest one you might think of to start off with is simply like forward backward Euler, where you have like the implicit part being just integrated backward Euler and the explicit part forward Euler. And there's also some more complicated schemes that you can drum up. To give a little bit like even more context, right? I mentioned at the outset that this is like kind of like a project within a project. So the main project that I've been working on at LLNL is topology optimization, specifically in the context of heat transfer. And specifically, one of the constraints in this optimization problem ends up becoming a advection diffusion equation. So in this context, what we wanted to do for the time integration is we wanted to use an IMEX scheme. And so since we wanted to use MFEM, we thought, okay, let's think of like a new framework for implementation of IMEX schemes into MFEM. Because while you can implement IMEX schemes in the current version of MFEM, the the framework that I'm going to be discussing today makes it a lot more nice. So in the context of advection diffusion, like I mentioned, you have a finite element spatial discretization. The advection term is not going to be positive semi-definite, and the diffusion term may be stiff, but it is PSD. So you might want to use an implicit scheme on the diffusion term, but an explicit scheme on the advection term. And what that works out to is that one, you get like a more relaxed CFL condition. So for example, instead of having a delta x squared time discretization, you need just like delta x. And on top of that, you don't necessarily need to invert the advection matrix, which is kind of nice. So let's talk about actual implementation. So in terms of the actual implementation, the current implementation for time-dependent operators in general in MFEM in its current state is we have this time-dependent operator class, which essentially, the way it works out is that time-dependent operators are this operator k. And specifically, we want k to solve the following equation, where you have like f on the left-hand side, which involves k, and some g on the right-hand side, which just involves u and t. And to kind of bring things down to earth, right? In the case of differential equations, k is just like your time derivative of your solution u, right? And to kind of bring things down to earth more, if you kind of want an idea of like, if you're not familiar with say like how this stuff works in MFEM at the moment, this f, for example, might be like your mass matrix times du dt, right? So that's like, and your right-hand side might be like, for example, the actual like differential equation. What we do is we have a new class, which is called split time dependent operators, which are of a similar form, but now k solves the equation f is going to be equal to some g1 plus some g2. So now you have like two parts on that right-hand side. Okay, so how is it different from just like, what are other ways in which it's different from just the time-dependent operator class? Well, time-dependent operator has two methods which are relevant to us. You have mult, which actually just performs the operation of the operator. And then you have implicit solve, which if you have some scalar gamma, is going to solve the equation shown here for k. In split time dependent operator, we kind of extend this. So we have a mult1 and a mult2, where mult1 and mult2 perform the operations of corresponding to g1 and g2, respectively. And then an implicit solve 1 and implicit solve 2, which solves the equation shown there for k. So you have like f equal to g1 and f equal to g2, where you have some scalar gamma. And so what's kind of nice about this is that while we specifically developed this for IMEX schemes, this can actually be used quite flexibly whenever you just have like any sort of split differential equation, right? So if you still want to use a fully explicit method, you use mult1 and mult2, right? Or if you want to use something fully implicit, you can use implicit solve 1, implicit solve 2, right? You're not forced to use, say, like something that's specifically IMEX, but this gives you some flexibility whenever you have some sort of split operator. And so the next part of the implementation is we have this subclass called split ODE solver, which essentially inherits from the ODE solver class that's currently in MFEM. So if you want to solve systems of the form, let's say du dt is equal to f1 plus f2, like we saw earlier, essentially what split ODE solver will do is it'll acknowledge the fact that that the ODE that you want to solve is split in some way, and it can account for that. As opposed to like currently an ODE solver, which like it just assumes that you just have your time dependent operator in the original version. And so the current implementation has the following schemes implemented. So you have like just a really simple like forward-backward Euler, including different Runge-Kutta schemes, right? Or different IMEX Runge-Kutta schemes that we have implemented. And in the future, what I would also like to do is to also implement some like multi-stage schemes. So currently, all I have implemented is all these are like, or they're all multi-stage schemes, but they're all like single step, right? So you have like one time step, you have like multiple stages, right? But then you go to your next time step and you're only reliant on the previous time step. In the future, what I would also like to do is to do like some sort of like multi-step scheme, right? Where you're like, where your next time step depends on like, say like a number of like previous time steps. So that's like one like future area that we can even extend this further. That requires playing around with, I think, ODE solver with stages, that particular class. So there could be like a couple of different changes have to be made, but it should be a relatively natural extension. Okay, so this is where kind of the fun part begins because I get to show you some videos, which is also why I wanted to use my own laptop. Essentially what we do is we have a PR, right? It's a work in progress PR, but essentially it has a new example 41, which essentially does solves like the time-dependent advection diffusion equation using a discontinuous Galerkin spatial discretization, and then the IMIX schemes that we have implemented as the time discretization, right? Which is kind of nice because currently there is a DG advection example code currently implemented, but there's not actually a DG advection diffusion. So, or not a DG advection diffusion in a time-dependent sense. So this is a new contribution we have, and it's a PR. So like if you want to recreate these results or play around with it or just give me some feedback, please, please do look at the PR. I will play the videos now. So I will show you some videos from various different domains. Let's start with this one, right? So this is just like a periodic, just like square essentially. So all the boundary conditions for these examples are going to be periodic because it was a little bit simpler to code. But look, you know, and we have like a predefined velocity field. We see like diffusion. We see like the effect of the velocity field, etc. We have a 3D case as well. So this is just like on a periodic cube. And as you're going to see, like the periodicity as a result. But like you see the diffusion, it's stable. So these are all done using the IMIX schemes that were implemented by us. And then I guess I had one more. This will stop. And then right here. And these are actually similar to the examples shown in the DG advection example. I think it's like an example 9, right? But now we have like this added diffusion as well. So, okay. And then, so those are kind of like that's what's been implemented so far. And then lastly, the way I do want to extend this is I mentioned earlier, this is like kind of a project within a project. So the next step in all of this, right? So this is kind of like, it's its own thing, but it's being used to build to something even bigger. The next step is now to use these newly implemented IMEX integrators for the context of, say, topology optimization. So when we're actually solving, let's say, the adjoint equations in time, we have these new IMEX schemes, which we're going to be working with, which is going to be pretty nice. When I talk about like project within the project, it feels kind of like, you know, like in those like superhero movies, like, you know, when like the hero finally defeats the bad guy, and now it's like, but like the very last scene is like some like even badder, more powerful guy, like gaining power, and like it's kind of like that. Like maybe at the next MFEM workshop, we also have like the topology optimization results there as well. But yeah, that's what I've been up to.
So I have a question for Topher. For the integration at the end that you showed, are you integrating over a surface for which you have mesh elements that the mesh is aligned with, or not?
Not necessarily. I'm integrating over a surface that much through mesh elements.
Okay. All right. And do you know about fine points? The way you can get data in general? Yes. Oh, yeah. Yes, I didn't even know we have a condo installation, to be honest. So that's just the standard condo installation was interesting. Okay, that's the scalable way to get data in a cloud, in a point cloud.
All right. Thanks.
I think, yeah, I have a similar question. I mean, same topics about integration. Looks like you are doing the integration on the surface. Can you transform that one, that integration, the boundary integration? Have you thought about that? Yeah, boundary is metallic boundary, right? Isn't it integrate same as the integration of the electric field on the boundary? Ah, sorry. Yeah, thank you.
Okay. Any other questions? Bill? Bill?
Hi, I have a question for Tony. I'm wondering how hard would it be to expand the interface you just created for arbitrary number of integrators, and if you have trial or what's your feeling on that? Like, do you think it makes sense to try more than 2 integrators?
So I haven't tried that. I think so the way it's currently implemented now, it does assume like you do have like just like 2 like integrators, like 2 parts. Like you have like, because it's just like molt1, molt2, implicit solve 1, implicit solve 2. So like, I guess the extension would be like, you would just have like a molt3, implicit solve 3. But I do see like, I guess like, I don't know of any applications where you might need like a lot more, but like I could see how like if I can't think of a scenario, but like if you did need like a lot, like maybe that might get out of hand. But no, I haven't thought beyond the number 2 yet.
Thing right behind you.
I guess this is also a question for you. Have you like thought about like extending this framework to solve like algebraic differential equations? So, like some parts are not time, I guess, not time-dependent constraints. Like there's a Poisson equation, for example, coupled with the advection equation or some other time-dependent PDE.
So like you're saying like kind of, if I can like understand it correctly, right? So like if you just have, I'm sorry, can you restate the question? I'm not like 100% sure. Oh, okay, I see. I haven't done any examples with that yet, but in solving the time-dependent part, I don't see why you couldn't use like this particular framework. But yeah, that would be something like to play around with. But I haven't like done that specifically yet. But I think like in solving the time-dependent portion, like it should transfer pretty nicely.